right, so we've talked about, or at least set up the idea that charges are going to interact via an electric force. To set that up, let's again think about what we learned last semester in 221 about the law of gravitation between point particles. So the law of gravitation told us that a gravitational force between 2 point particles with masses m1 and m2 separated by a distance r has the following properties. So A, it's going to be directed along the line joining the 2 particles. So notice that here's mass 1, here's the force, the gravitational force felt by mass 1 caused by mass 2. Here's mass 2, here's the force, the gravitational force felt by mass 2 caused by mass 1. So notice that I'm really drawing 2 free body diagrams here. One for mass 1 with its force that it feels, one for mass 2 with the gravitational force that it feels. And both of those forces lie along the line that's connecting those 2 masses. It's attractive. Gravitational force is always attractive. And then it has a magnitude that's given by the following expression. So the magnitude of the gravitational force is equal to big G, which is the gravitational constant, it's just a number, the product of the 2 masses times the distance between them squared. So here's r, the distance separating our masses squared. And one of the things that we talk about all the time with gravitation is because big G is such a small number, right? -11. This is another way of saying basically 66.7 billionths. So this is a tiny number. So because G is small, the gravitational force ends up being very weak. All right, so let's look at Coulomb's law now. And what Coulomb's law tells us is that an electric force between 2 particles with charges Q1 and Q2 that are separated by a distance r has the following properties. So notice Coulomb's law is already set up very much like the universal law of gravitation. So here are my 2 charges. Here's Q1, here's Q2. Notice in this case, Q1 and 2Q are oppositely charged. In this case, Q1 and 2Q have the same charge. And we know from what we've already laid out about charges that opposite charges are going to attract. So here's the electric force felt by charge 1 caused by charge 2 that is attractive. So charge 2 pulls, in this case, charge 2 as an opposite charge, pulls charge 1 towards it. Here's the electric force felt by charge 2 caused by charge 1. And again, because these are oppositely charged, it's being pulled towards charge 1. Here, in the scenario on the right-hand side, the 2 charges have the same charge. So notice that those 2 forces point opposite. So again, charge 1 here is being repelled by charge 2 because it has the same charge, and charge 2 is being repelled by charge 1. So each of these is sort of its own free body diagram for the electric force on each of these 4 charges. So Coulomb's law says that this electric force has the following properties. The first one is it's directed along the line joining the 2 particles. So notice in the attractive case, those 2 forces point along the line connecting our two charges. In the repulsive case, those forces still lie along the line connecting those 2 particles. They just point away rather than pointing towards. So obviously the second part is that those 2 charges can be either attractive or repulsive. So that force can be attractive or repulsive based on whether those 2 charges are the same or different. And again, as we've talked about before, this is why we need 2 types of charge. It takes 2 types of charge, which we have simply labeled positive and negative, to explain a single force that is both attractive and repulsive. And then 3, Coulomb's law tells us that the force that these 2 particles, these 2 charges exert on each other has a magnitude given by the following expression. So the magnitude of the electric force is equal to, here's a constant called the Coulomb's constant. It's usually denoted by K sub E or sometimes just K, They will often write the sub E to make sure we don't confuse it with the spring constant. And the Coulomb's constant is basically 9 times 10 to the 9th Newton meters squared per Coulomb squared. So again, one thing here is, A, this constant is really, really large. This is basically 9 billion. The other thing is that I'm going to multiply this constant by a product of charges. That's going to have units of coulombs. That's going to have units of coulombs. So notice in the top of this fraction, my product of charges is going to give me Coulomb squared. That's going to cancel that. I'm going to then divide by a distance squared. So that's going to give me meters squared on the bottom. That's going to cancel that. So the other function of the Coulomb's constant is to convert this product of charges divided by a distance squared into a force. That's what this unit effectively does. So there's my Coulomb's constant. Notice with my product of charges, both of these are in absolute values. And again, this is the one really important, or certainly one of the really important differences between Coulomb's law and the uniform law of gravitation. In gravitation, I had two masses. Those two masses were always positive. Here, I want a magnitude of a vector. Magnitude of a vector is always a positive quantity. This number is positive. A distance squared is positive. So both these need to be positive. So this is why I end up not worrying about the signs of my charge, of each of the charges, when I'm calculating the magnitude of the force. So a couple of additional things about Coulomb's law. So for starters, again, this emphasizes that all forces are interactions between two objects. Here, the electric force is an interaction between two charges. That's why I need Q1 and Q2 in this expression. Part of what this tells me then is that objects feel an electric force because they have charge. So if you had a neutral object, an object that doesn't have charge, it would never feel an electric force. So I need objects to be charged to feel the electric force. Second important thing the Coulomb's law tells me is that because this is 1 over r squared, and again, we wrote it as r squared on the previous page, here we're writing it as r12 squared, there's not any important distinction. Both of those are really just ways of saying the distance between particle charge 1 and charge 2. So whether we write this as r squared or r12 squared, don't let that throw you off. They're absolutely equivalent. But since this is basically some group of numbers times 1 over r squared, that means that the larger the distances between our two objects, the weaker the electric force gets. So when you make the distance between them bigger, you're dividing by a bigger number squared, which means the magnitude of your force is going to get smaller. And it's going to get smaller in a very special way, because if you double the distance between your 2-point charges, then the electric force is going to be 1 over 2 squared, or 1/4 its initial value. So when I increase the distance, I'm going to increase it in exactly the way so that it's going to be 1 over that distance squared. So this is what's known as an inverse square law. And again, this is just the same form, exactly the same form that the universal law of gravitation had. So the next thing that Coulomb's law tells me is, again, think about our constant K. And again, here we've written it as K rather than KE. And in the same way that this is R versus R sub 1, 2, it doesn't, we're going to be, those things get used interchangeably. So don't let that throw you off. But because K is a really big number and G was a really small number, electric forces are much, much stronger than gravitational forces. So even though, obviously when you drop something, it falls, gravity is actually a really weak force. It takes very, very large masses to notice gravitational forces. Because K is very, very large, we don't actually need big charges to end up with very large forces. So I can get really strong electric forces between pretty small amounts of charge. And so we'll deal with charges that are often microcoulombs, 10 to the minus 6, nanocoulombs, 10 to the minus 9, maybe even picocoulombs, 10 to the minus 12. So very, very small charges will still result in very large forces. Now, let's go ahead and introduce at this point that the Coulomb's constant is related to another universal constant that we're going to end up seeing a lot, which is known as the permittivity of free space. It's epsilon naught. So this is a lowercase Greek epsilon. That's a zero subscript. And notice that the Coulomb's constant is 1 over 4 pi times epsilon naught. So we'll see epsilon naught a lot, basically when we're working with electricity. There's another constant that we'll see a lot when we're working with magnetism. So epsilon naught is our electricity constant, and just because it's not sitting here explicitly in Coulomb's law doesn't mean it's not there. It's folded into K. And so its value, right, epsilon naught's value is 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. All right, so sort of the last thing that's critically important to take away from Coulomb's law is, again, we're being a little bit sloppy here. This is really a way of saying the magnitude of a force vector. Well, all forces are vectors. Electric forces are vectors. So we got to remember that when we're dealing with forces, we got to do vector stuff. So when we want to add electric forces, they have to be summed as vectors. So electric forces, just like any other force, it's a vector problem. So we've got to do vector things. The important difference here is that the signs of the components of your electric force are determined by your choice of coordinate systems. This absolute value makes the signs of the charge not matter in terms of calculating this magnitude. So whether it's positive or negative is going to depend on whether, for these particular charges, that force is attractive or repulsive, and your choice of coordinate system. So did you pick the direction of their force to be in the positive direction, or did you pick the direction of their force to be in the negative direction? So this is a vector problem just the same way that any sum of the forces is a vector problem.